Gadde on conformal constraints on defects.
Thank you very much for the invitation to this wonderful conference. Today I'll be talking about constraints imposed by conformal symmetry on extended operators in conform field theory, also known as defects. A conform field theory is just a quantum field theory, but in addition to translation and rotational symmetry, it has scale invariance, x going to lambda times x, and invariance under special conformal transformations. So these transformations you can think of as translation conjugated by inversions. Although it's not apparent from this nonlinear action of the conformal group on the coordinates x, the conform group actually for a d-dimensional Euclidean conform field theory is very simple. It's simply SOD plus 1, 1. It's the scale invariance that gives rise to a very interesting and important property of a CFT, namely the correspondence between states and operators. In any quantum field theory, if you are given a local operator, one can define a state associated to it by performing a path integral over a ball to get a functional of the boundary values, giving a state. But in the CFT, the correspondence also goes the other way. Given a state, you can collapse the sphere using the scale transformation to a point, and at that point, you can model the state by an insertion of a local operator. So that's why it's very natural and usual to formulate CFT in terms of local operators O of x and their correlations. These correlations are greatly constrained by conformal symmetry. These constraints are very well known. They've been studied to a great extent. For example, the 2-point function of local operators is completely fixed, and the 3-point function is fixed up to a numerical constant. And the higher point functions of these local operators are then determined in terms of these structure constants. In addition to local operators, conform field theories also have another interesting class of operators, namely extended operators or defects. So some of the familiar defects are Wilson and 't line operators in gauge theories, surface operators, or domain walls or Janus type walls, monodromy defects, or if the CFT comes from a lattice, there could be edge dislocations in the lattice, or even boundaries. All these can be thought of as defects in the formalism that I'm presenting. So in this talk, I'll be interested in a rather symmetric class of defects, what I call conformal defects. These are defects that preserve the maximum symmetry. So for example, if you have a codimension M defect in a d-dimensional CFT, I wanted to preserve this particular subgroup of the full conformal group. This SOM is the rotational symmetry transverse to the defect, and SOD minus M plus 1, 1 is the conformal action in the directions parallel to the defect. As the symmetry suggests, the defect could be a plane, or in fact, it could even be a sphere. In order to go from the plane to a sphere, you simply need to act on it by special conformal transformations that point in the transverse direction. They curve the defect into a sphere, so the statement is that these conformal defects that I'm talking about generically are of spherical shape. Now, when I say that I want to study constraints of conformal symmetry on correlations of defects, it is most straightforward to do in what is known as the embedding space. That is the space where the action of the conformal group is realized linearly, as opposed to the real space where I saw the transformations. They were quite nonlinear. So the form of the conformal symmetry group, SOD plus 1, 1, suggests that it has a linear action on a d plus 2 dimensional Minkowski space, and this is known as the embedding space. Now, in order to go from the embedding space to the original space, d-dimensional space, we need to get rid of 2 dimensions of this Minkowski space in a SOD plus 1, 1 covariant manner. And the way to do that is to consider the null cone. This is simply defining a light ray up to a projective identification. Both these equations, you can see, are SOD plus 1, 1 invariant, and each of them gets rid of one dimension. Just to fix some notation, in the embedding space, I denote the vectors in the light cone as follows: x plus, x minus, and xi, where I goes from 1 to d, which is the original dimension of the CFT. And this is the metric on the embedding space. Now, in this slide, this is just a graphical presentation of what I just said. We have this as an embedding space. The null condition carves out a light cone, and projective identification means that a light ray corresponds to a point in the original space. Now, this projective identification can be taken care of by fixing a gauge, x plus equals 1, which cuts out this particular slice, which is also known as the Poincare section. And when you solve this condition, x plus equals 1 and x dot x equals 0, you get x to be of this form. And as you can see, the points on this Poincare section are then in one-to-one correspondence with the points in the original d-dimensional space. Now, there is yet another light ray which does not intersect this Poincare section, namely the ray that is tangent here. And from the point of view of the original d-dimensional space, that's simply the point at infinity. So one can normalize this point like so, and I denote this with a special letter omega, and this is the point at infinity when you conformally map the RD to the sphere. And also the usefulness of embedding space here is apparent when you note that the distance between 2 points x and y is given by the inner product x dot y. So it's linear in both x and y. So the linearity is already apparent in the distance. Now, as I said, the defects that I want to consider are objects that preserve the codimension M defects that I want to consider are the objects that preserve SOM times SOD minus M plus 1, 1. So it's clear what they should be in the embedding space. These are simply flat hypersurfaces that pass through origin in the embedding space, and they have a certain intersection with the null cone and with the Poincare section, and that defines our defect in the original space. So in order to specify the position of the defect, it also means that I want to specify the position of the hypersurface in the embedding space, and that I can do by specifying M transverse vectors. So they could serve as the defect coordinates P alpha, but only up to a gauge redundancy GLM, which redefines the P alpha with a linear map. Now, this gauge redundancy can be partially gotten rid of by choosing P alpha to be an orthonormal frame, but that still has an OM worth of gauge redundancy. So all in all, I would be coordinatizing the defect by specifying an orthonormal frame with an OM redundancy. And this would be the notation of the defect. I'll be dropping this OM often, the position of the defect. Now, as described earlier, the defect locus in the embedding space is simply the points x, which are null, and also lie on the Poincare section with the transversality condition P alpha dot x. Now, let's see what this locus means in the original space. Now, to start with, we just take codimension 1 defect. So we take M equals 1. So we only have one vector P dot x equals 0, and this transversality condition translates into this. And this is simply an equation of a codimension 1 sphere of radius mod P divided by P plus and centered at Pi divided by P plus. Now it's clear what it means for general M. General M is simply M conditions of this type. So the final locus that we get is going to be intersection of M codimension 1 spheres, which is simply a codimension M sphere. So from this exercise, it's clear that the defect, a conformal defect that preserves the maximum symmetry that I want is going to be a codimension M sphere in general. Now, the center and the radius of this codimension M sphere can be fixed in a closed form using the OM gauge redundancy that I was talking about. So imagine, if you wish, a problem in coordinate geometry where you are given a bunch of codimension M spheres and are asked to find the center and the radius of the sphere that you obtain after intersecting all of them. If you just were to use coordinate geometry, it's a cumbersome problem. But in this approach, you simply write down gauge invariant and SO d plus 1 comma invariant combination of the coordinate P alpha to get a vector and to get a scalar. Well, that is not possible, because in conformal field theory, the notion of distance is not absolute. You need some reference point, and the point at infinity serves as the reference point. So what you need to do is, along with P alpha, you are also allowed to use omega, which is the point at infinity, and simply there is only one combination that you can write down as a candidate vector, and that is the center of the final defect, and this is the only scalar combination which serves as the radius of the defect. Now, we can consider the correlation function of a local operator in the presence of defect. So this is the geometry that I have in mind. You have a defect, next to it is a local operator, and then I'm interested in finding this correlation function. Now, because the conformal symmetry is realized very linearly on X as well as on P, one simply wants to write down a combination of X and P which is consistent with conformal symmetry and is invariant under the OM gauge redundancy. And there's a unique combination that one can write down. It's this. And of course, there is a constant that is not determined by conformal symmetry, which plays the role similar to the 3-point function constant or structure constant in the case of three local operators. So this I call CDO, which means the D is the label for the defect and O is the label for the local operator. Now, this is slightly obscure. You don't quite know what's going on in the real space. You can translate it, and this means that if L min and L max are the minimum and maximum distances respectively of the local operator from the defect, the spherical defect, then the 2-point function is simply given by L min times L max divided by 2r to the power minus delta O, which is the conformal dimension. This expression simplifies if you take the defect to be a flat one, and that can be done by taking L max going to infinity along with the radius of the defect. So in addition to tending to infinity, they both tend to each other, so you can cancel them, and you simply get, for a flat defect, the 2-point function to be this. Now, the fact that conformal symmetry completely fixes the correlation function of a defect and a local operator up to a constant gives rise to a notion, what you could call the defect expansion, which is very similar to the operator product expansion. So the idea is to surround a defect by a spatial slice and study the state on it and contract it to a point and expand that into local operators. So this is what I call the defect expansion. And here, the strength with which the defect D expands into local operator O is exactly the CDO, the structure constant that we talked about earlier. And of course, this expansion has a very specific tower of descendants, which encode the symmetries of the defect. And this expansion, as you can see, is very similar in spirit to the operator product expansion. Now, with this operator product expansion at our hands, we can now consider the case of a correlation function of two defects. So here, I'm interested in studying the correlation of defect labeled by P alpha and another defect labeled by Q mu This is codimension M, while this is codimension K. This is a schematic picture of the geometry. This defect has this expansion, while this defect has a very similar expansion, and now one can simply take the 2-point function of these two expansions. Of course, this is quite cumbersome to carry it out. In practice, there is a much better and cleaner way, faster way to do that. But before going to that, let us note that the correlation function of two defects, unlike the previous case, depends on a number of conformally invariant quantities known as conformal cross ratios. So first of all, we need to understand what are the conformal cross ratios associated to the geometry of codimension M and codimension K defect in a d-dimensional conformal field theory. Now, to understand these cross ratios in the original d-dimensional space is a bit difficult because, again, for the nonlinearity, but we know what's going on in the embedding space. A codimension M defect lifts to a codimension M hyperplane, while similarly for codimension K defect, schematically represented by line. And then the conformal cross ratios are simply the parameters needed to specify the relative position of this hyperplane with respect to this hyperplane. In other words, these are simply angles between the two. So the angles can be encoded in the matrix of angles M alpha mu, which is just the dot product of P alpha dot Q mu. And this is an M by K matrix. But now remember that P alpha and Q mu were only meaningful up to OM and OK respectively. So one can use that redundancy to simplify this matrix by setting these lower triangles and upper triangles to 0, essentially remaining only with the leading diagonal. And from here, it's clear that the number of parameters required to specify this position is the minimum of M and K. Now over here, I've assumed that the planes spanned by P and Q intersect only at one point. But that need not be the case in general. They could also intersect if M and K are bigger than 2D, I guess, then they could also intersect at a multidimensional subspace. In that case, you simply consider transverse planes to these guys. They have dimensions d plus 2 minus m and d plus 2 minus k. And a very similar argument as before tells you that the number of cross ratios is minimum of d plus 2 minus m and d plus 2 minus k. All in all, you can write down a simple formula like this, that the number of cross ratios is minimum of mk, d plus 2 minus m, and d plus 2 minus k. Now, these cross ratios can be extracted in a gauge invariant fashion from the matrix of angles that I had written down, M alpha mu, by taking traces of various products of M transpose M. Here the I go from 1 to the number of cross ratios that I just talked about in the previous slide. So now let us go back to the 2-point function that I'm interested in computing, d of P alpha and d prime at Q mu. This is the expression that we get after expanding both of these defects into local operators. But finally, this is what we end up with, that you have the strength with which O appears in the expansion of D, the strength with O appears in the expansion of D prime, times a function that depends only on the conformal cross ratios. This is known as the conformal block, and one can compute this by solving a differential equation, namely the conformal Casimir equation. So the way one gets it is by imposing conformal invariance of the 2-point function of defects, and this is the equation that the conform block needs to satisfy, where these LABs are the generators of the SOD plus 1 comma 1. In terms of P, they are given like so. But these functions are functions of eta I, so we need to change this into the equation for eta I. And the equation that we get finally looks like so. Here there are a bunch of dotted terms which look very similar to these ones, but I haven't written down. Perhaps it's not very illuminating. But you get a pretty complicated looking equation in terms of cross ratios like this. Now, of course, the mathematics of these equations itself turns out to be quite interesting. But in the talk, I will simply give you some examples of the solutions. So consider the case of codimension 1 defect close to a codimension M defect. So this codimension 1 defect here could as well be a boundary. And codimension M defect, one special case is when M equals to D. And in that case, codimension D defect is simply a pair of points. So a special case of this scenario is simply when you have 2 points near a boundary. And in that case, you can simply, the differential equation simplifies quite a bit and turns out to be a Gauss hypergeometric equation. And this is the solution that you get. And this agrees with the bulk conformal block that people talk about in the case of M equals D. Now, another interesting case which could have applications for, say, computing entanglement entropy or Rényi entropy for 2 disconnected regions is the case of 2 codimension 2 defects. In this case, the number of cross ratios turn out to be 2. Now, that sounds familiar because the number of cross ratios for 4 local operators is also 2. And turns out it's not a coincidence. You can, in fact, map the equation that you get for the case of codimension 2 defects to the equation that you get for 4 points. And this problem has already been solved, has been considered and solved by Dolan and Osborne. And the conform blocks, for example, say in 4 dimensions, are, so this would then be a correlation function of 2 surface operators in 4 dimensions are given by products of hypergeometric functions, so on. Okay, so let me leave you with a problem that I consider interesting as well as important. So one has, when we say that the correlation function of local operators is completely fixed by conformal symmetry, not only is it fixed in terms of 3-point functions, but even that data is fixed using what we know, what we call the crossing equation, which is an equation saying that the 4-point function of 4 local operators you can compute either by quantizing on this sphere here or on this sphere. And these 2 equations, the equality of these 2 possibilities gives rise to a very constraining equation, which there has been a lot of activity recently to solve and constrain the spectrum of the CFT itself. Now, what would be the analog of crossing equation in this case, where you have 2-point function of 2 defects? The correlation, the way I computed the correlation is by quantizing the CFT on this particular slice. But could there be another slice on which one can quantize the CFT to get an alternative computation? By equating them, perhaps one can hope to constrain the spectrum of defects in a generic CFT itself. Okay, let me stop here. Thank you.
Thank you. Are there questions?
What can you say about the structure of singularities in these correlation functions?
Yeah, the singularities appear well, it's not quite clear from the way I have computed the correlation function by quantizing, say, on this slice. But it seems that the singularities would appear when the defects touch each other. But this expansion won't tell you much about that limit.
Other other questions? Well, yeah.
Is there a difference between the codimension D defect and the local operator?
No. So a codimension D defect would map to a pair of local operators.
Whose distance is arbitrary?
Yeah, because codimension M defect in general is a sphere, so codimension D defect would then be a sphere of 0 dimensions, which is just 2 points, and depending on the radius of the defect, that would control the separation between the 2 points.
Okay, then let's thank the speaker again.
Thank you.